Yeah, good morning. We have seen this logic CTL. The idea is that you reason about these computation trees. So we have seen this logic reasoning about trees. We have seen the difference with LTL. What is at stake today is the model checking problem. So input a finite transition system, input a CTL formula, question, does your transition system satisfy the formula or not? And we're going to see a polynomial time algorithm today to do this checking. So what's the idea? The idea is that we're going to compute recursively the set of states satisfying a formula. So what we are going to do is we take this CTL formula S and we're going to compute the set of states satisfying this formula. And then what we need to do is, in order to check whether the transition system satisfies the formula, we need to check whether every initial state is included in this set of states satisfying phi. Good, so the way to do that is actually as follows. We first decompose, we just look at the parse tree of the formula phi, we look at the subformulas of it, and we compute the set of states satisfying this subformula. So the strategy will be that we do the inner subformulas first, and that's exactly the strategy that we did when I was discussing several examples to see whether a transition system satisfies a CTL formula. So we do this from inside out. And then you can say the following: we replace this subformula by a new atomic proposition. And then what we do is for every state satisfying this subformula, we basically extend the labeling of that state with this new atomic proposition. And finally, what we need to check, if all initial states satisfy phi, then the output is yes, and otherwise the output is no. Yeah. I'm not going to talk about counterexamples in CTL. That's a bit more hairy than for LTL. That's quite much more advanced. Good, so let's here take an example. There exists a path which has as next state an A state, or there exists a path which satisfies B until not C. So we look at the parse tree of the formula. This looks as follows. The topmost operator is the disjunction. It has as left argument there exists next with A, and as right argument there exists, so an existential path formula with the until modality, where the left one is B, and the right argument is not C. Good. Then what we're going to do is, in terms of the parse tree, we're going to do a recursive descent, which means you start with the leaves, in this case A, B, C. We're going to compute the set of states satisfying A, satisfying B, satisfying C. Now this is trivial, because this you can just look up from the labeling of those states. So then what you're going to do, you go one level up in the tree. So suppose that now we have computed the set of states satisfying A, then we can now recursively compute the set of states for existential next. Because what are the states satisfying existential next? Those are those states that have at least one transition into the state satisfying A. Now I have this state already there, I have it identified, so the only thing I have to do is, does my state have at least one transition into that set or not? Good. For negation, it's easy because you just take the complement. If I have the set of states satisfying C, the set of states satisfying not C is just the complement. For phi 2, it's a little bit more complicated, as we're going to see. And actually, we're going to do a fixed point computation. Expansion law. So very similar to LTL, the expansion law will be the core for this operation until. So what we're going to do is we replace, suppose that I have computed the set of states satisfying this blue subformula and as well for the green. Then what I do is, syntactically, I replace this formula with an atomic proposition A1, the other one with A2. So that's the situation now. I have this formula, and now I can compute the set of states satisfying the root of the tree, which is the end result we are interested in, which is just the union of the set of states satisfying the blue formula and the green formula. Good. The main ingredient will be the existential until and as well the existential box. So this is what we're going to do. We're going to compute these set states, And what I'm going to do is I'm going to explain this procedure for the fact that C is an existential normal form. Yeah? So I'm going to assume that the only formulas occurring in my CTL formula are of the form existential next, existential box, existential until. No universal quantification. I know that the existential normal form can be longer than the original form, yeah? And you can do the same reasoning for universally quantified formulas, but for simplicity, I only do the explanations for existential normal form. Good, so analogous algorithms can be designed for universally quantified formulas. So it's only for the presentation that we do the simplification. It's not the case that in practice you first always have to transform your formula into existential normal form. Good, so what's existential normal form? We only have those three modalities. So that's exactly what is the syntax. And remember that you can transform every CTL formula into a CTL formula in existential normal form. The drawback being that, for instance, if you have a universally quantified until formula, you get a very long existentially quantified formula. For the moment, as I said, I only want to conceptually explain you the algorithms for existential next, existential until, and existential box. The other algorithms are actually very much similar. So this blow up in the formula doesn't bother me today. So how are we going to recursively compute this? Well, this is just by induction over the structure of the formulas. So we're going to look at the state formulas, and we start with the most simple one is just true, and the set of states satisfying true is the entire set of states of my transition system. What is the set of states satisfying A? Those are all states in my transition system that are labeled with A. What are all states satisfying not phi? This is the complement of all states satisfying phi. Conjunction is just intersection of the two sets. What about existential next? So these are all states that have a direct successor which is satisfying phi. So stated differently, post S, the set of direct successors of S, intersected with the set of states satisfying phi is non-empty. It has at least one transition to a phi state. So how can I decide this? Well, you just look at this state. Remember, you do the recursive descent, so this set is at your disposal. You have already computed this because of this bottom-up computation. Yeah? So the only thing you have to do is indeed check whether such a state has a transition into this set or not. So that's relatively easy. And for until and box, we're going to do a fixed point computation. Good. And these fixed point computations will be different in the following sense. It's similar to what we have seen for LTL. So, intuition. What we're going to see is existential until is a least fixed point. Remember the expansion law, also there until was a least fixed point of a fixed point equation. So how are we going to compute this least fixed point? What you're going to do, you are going to compute successive under approximations. So intuitively this is very easy. If you start with something of the form existential A until B, right? How would you compute this intuitively if this is your stalled transition system? Well, the first thing you know is that all B states satisfy this formula. So let's start with the B states. So you first identify the B states. Yeah, so this is the set of states satisfying B. And then, what do we need to do? Well, in the next step, we're going to check all the A states that have at least one transition to a B state. Yeah, so in the next iteration, you're going to take all the A states. Yeah, so they are all satisfying A. But all these guys have at least, they can have several transitions, but at least they have one transition into this area. Well, these states definitely also satisfy the formula. So let's add them. right? So now what you get is you get this set of states. Yeah. Now what are you going to do? So this is basically the set of states that where you have A and existential next B. Yeah. And now you do this recursively backwards. So now you look at what other A states, maybe there is an A state here which has a transition into there. But that's okay, because now I can construct a path that goes from A to an A state and then to a B state, so it has a path that goes from A to B. So I can add this state as well. Yeah, that's the intuition. So you approximate from below. You start with this set for which you surely know that the formula holds, and you try to extend it. This must terminate. Why does it terminate? Because we only have finitely many states. Yeah. Good. So what are we going to see for existential box? Existential box is what they call a greatest fixed point. Yeah. So what are we going to do with greatest fixed points? You're going to approximate them from, not from below, but from above. So they are we going to compute successive over approximations. Yeah, so here is over and here is under. Yeah. So what does that mean in terms of a computation? You start with a set and you're going to try to make it smaller and smaller and smaller until you end up with the set of states that you are interested in, the set of states satisfying this formula. So how does this look like in terms of a picture? Suppose that I'm interested in existential box A. Yeah, you start with your transition system. Suppose this is my transition system. The first thing you're going to say, well, what's an over approximation of this? Well, I'll pick all the A states. Yeah, because those potentially could satisfy this formula. Yeah, so I take all the A states. So this is SAT A. Good. Now what I need to do is, here is an A state. Yeah, here is another A state, here is another A state, here is another A state. What do I need to check? Well, I need to check whether this guy, this state, well, it maybe have a transition outside to this state, that's okay, but it has to have at least one transition there in order to fulfill the formula. Yeah? If such a transition is not there, it cannot satisfy the formula. So what are we going to check? If this state has only transitions going outside, we eliminate it. Yeah? So if this one maybe has a transition here, that's okay. Yeah? That can have a transition there. But if this one only has transitions there, the first thing I'm going to decide, well, that one needs to go out, because it's not going to satisfy their exister part, which is only consisting of A states. Yeah? And now you see, can I reason this backwards again? Because now this state, if this is the only transition this state has, it cannot fulfill this formula because this state does not fulfill the formula. So I have now to eliminate that state. Is this principle clear? So now in the next state, we're going to eliminate that one. So successively, we start with a very, let's say, angelic over approximation. All A states potentially will satisfy the formula, and then we're going to make this set smaller and smaller and smaller. Does this terminate? Of course it terminates because we only have finitely many states. Good. That's the intuition. Let's look at the details in a minute. So remember the expansion law. The expansion law for CTL says there exists a path satisfying phi 1 until phi 2, if and only if the current state satisfies phi 2, or if this is not the case, it needs to satisfy phi 1 and needs to have at least one successor satisfying the until formula. Good. So what does that mean? In terms of sets, this can be written as follows. So just read this in terms of a set. So suppose I'm interested in the set of states satisfying this formula. Yeah, the set of states satisfying this formula equals, the set of states satisfying this formula, or union, the set of states satisfying this formula. What is this? Well, it means that your state has to fulfill phi 1. So we are currently interested in states satisfying phi 1. And what else? There exists a next state, which means this state, S, needs to have a direct successor moving to a state satisfying the remaining formula. So the direct successors of S intersected with the set of states satisfying the formula needs to be non-empty. This is the same trick as I had before, existential next. Good. Now again, this is a fixed point. This is no surprise because this is what we extensively discussed for LTL. This formula on the left occurs in the same shape on the right. So in terms of sets we have this and the same principle. This set occurs on the left, but it also occurs on the right. So what actually it means is the set that we are looking for, this set, is a fixed point of a higher order function. It's a function that maps sets of states to sets of states. And this function, basically read this as follows. Read this as a parameter, t. Then this function applied to t gives you the right-hand side. What does that mean? It tells you sat phi 2 union all phi 1 states that have at least one successor into t. This function may have several sets for which omega of that set equals omega, equals that set. So again, omega is a function, so you can have several x's for which omega x equals x. These are all fixed points, right? And now we're going to argue is that the fixed point that we are interested in is the least fixed point. So we're interested in the smallest set satisfying this. Good. So what does that mean? This set satisfies the following conditions. Well, you see immediately it needs to include all the phi 2 states. So all the phi 2 states must be included in the set that we're looking for. Further on, the second condition says, if you give me a phi 1 state which has a direct successor into the set, then that also should be member of that set. So that's the second condition. If you give me a phi 1 state which has a direct successor that goes into the set of states we are looking for, then that state needs to be in the set we are constructing. That's basically what the second part of the union tells you. Now what we're going to do, the set of this thing is the smallest set such that 1 and 2 hold. So how can we see this? What I want to show is the following. So sat existential phi 1 until psi is basically the smallest t, which is a set of states, such that the following two conditions hold. 1, sat phi psi is included in t, and 2 says that if S is a phi state and it has a direct successor into t, this implies that S belongs to t. Good. I'm concentrating on so it's definitely it's easy to see that this is in a sense correct. What I'm going to argue is the following. I'm going to show the smallest thing. So let's prove. I'm going to prove that this is the smallest. I mean that this set is correct immediately follows from the expansion law. Yeah, because it satisfies the first constraint and the second constraint, so that's definitely correct. That directly follows from the expansion law. So the first thing, how about the smallest thing? So let t satisfy 1 and 2. To prove t is a subset of sat existential phi until psi. Good. Two cases. So I'm going to say let S be a member of this set. A S belongs to sat of psi. but that's easy. S sat psi subset T, then also S belongs to T. So this is what I need to prove. Second case, S does not belong to sat of psi. Then there exists a path starting in S so this equals S. Such that pi satisfies phi until psi. I want to prove that T is the smallest thing, right? And this is what I want to prove. Yeah? Yeah, maybe I was a bit quick. This is part B. I mean, part A is that you say, well, T is the sat of existential phi until psi. And then you have to show that this indeed follows then T satisfies 1 and 2. Yeah. And this follows from the expansion law. That's the part I skipped. Yeah. And now I want to show that if I have such a T, that it's the smallest one. Yeah? So this part is there. Right. So let n be larger than 0. And you assume that Si satisfies phi for all I less than n, and Sn satisfies psi. Then we have that Sn belongs to the sat of psi, because this holds. And then what we need, so that means that it belongs to T. Sn minus 1 belongs to T, since there is a path Sn is a direct successor of Sn minus 1, and that's in T, and we know that Sn belongs to T. Sn minus 1 belongs to sat of phi. And this you can go back, so in the end you can get something like S0 belongs to T, since S0 belongs to post S1 that intersected with T, and S0 belongs to sat of phi. So what we have is that S0 belongs to T. Good. Yes?
I'm sorry, but I think there's still some things swapped around. Like in the last line, it's S1 is a successor of S0, right?
Yeah, okay. This, yeah, absolutely right. Yeah, here I missed the N and N1. Here this should be a 1 and a 0. Yeah, very good.
Also still, what you're showing is that if we have a state in the satisfaction set, then it's also contained in T. So I think the proof is indeed for the comment that my colleague made, that the satisfaction set is always included in T. Which would make sense, right?
Yes. Yeah. Yeah, because you start with a state satisfying in this, and then you prove that it is in T, right? So the only thing we include is the other way around. Yeah, it seems I'm not awake yet. Yeah. Yeah. Good. That was the until. What about existential always? So existential box is the largest set satisfying the following criterion. So we're looking for the set V, and V needs to include all the states that are satisfying phi who have a direct successor into V. Good. So in terms of a fixed point, this is similar as we had seen on the previous slide. This is a fixed point of a function. And this function takes as argument a set of states, right? And think about, for instance, this set of states, a set of states satisfying existential box phi. And it gives you a set of states. And the idea is that omega of V gives you the set of phi states which have a direct successor into V. So let's look at an example. This transition system of 3 states. We are interested of existential box A. So if you take the set of states S0 and plug it in here, S0 is a subset of all the blue states who have a direct successor to a blue state. Yeah? Well, to a state in V, namely S0 itself. Yeah? So because of the self loop, the fact is that the set S0 satisfies the inequation. But this is not the set of states satisfying the formula, because of course also S1 satisfies the formula. There exists a path which is completely blue by just taking the self loop. Yeah, so we're not interested in just an arbitrary set satisfying this criterion, but we're interested in the largest set. Yeah? We need to include in this example S1, because S1 also satisfies this formula. Good. I'm going to skip the weak until because that's not so much important. So the fixed point equations for existential until that we just have seen is the smallest set. So here is an example. Why do we need the smallest set? So let's consider this transition system. The set of states, for instance, S0, S1, S2, satisfies star. So let's check this. This is a set of states. So ignore the smallest. It's just a set of states satisfying. We have to include all the B states, right? That's S2, and we have to include all the green state, and we have to include all the blue states, which is S0, S1, which have a direct successor into T. Now, if this is T, S0 has a direct successor into T because it can move to S2, for instance, and S1 because of the self loop. Yeah? So this satisfies this criterion. But it's not the smallest set. So look at the formula. There exists A until B. Which states satisfy that formula? Well, definitely the B state and also S0. But this state, which we included into T, which satisfying star, does of course not satisfy the formula because it has no path reaching the green state. Yeah? So this is an example that shows you that you cannot take any arbitrary set satisfying this criterion. You're here interested in the smallest set satisfying the criterion. Good. For weak until, the situation is very similar as in LTL. The weak until satisfies the same fixed point equation, but this is the greatest set. So for the weak until, again, you have to take the largest set, can look at an example. So if you have something of the form A weak until B, and you look only at this second criterion, you take all the states that include all the B states, so definitely S2 should be there, and you take all the A states which have a direct successor into this, which then includes S0 because that's a blue state and it has a direct successor to S2. That satisfies this formula, satisfies this criterion, but it's not the set of states satisfying this formula because S1 also satisfies the formula because we know that the weak until is also satisfied if there exists a part which is only blue, and that means that we have to add S1 to that set. So therefore we cannot take an arbitrary set, but we really have to take the largest set. Good. One remark about universally quantified formulas. So if you do not, let's say, only restrict to existential normal form, then you are interested in doing the direct computation on universally quantified formulas. So the satisfaction set of for all box A simply means you take all the states that only have direct successors which are satisfying A. So that's the situation. For all box, that's very similar as existential box. It's the greatest set of states. The difference being that it's not sufficient to have only one transition into T, but you have to require that all direct successors are included into T. Yeah. Good. And for all until, it's also characterized as a smallest fixed point, so it's a smallest set. It's similar as before. You take all the B states that need to be definitely in this set because all the B states satisfy this formula, plus you take all the blue states satisfying A that only have direct successors which belong to T. Yeah? So the principle is very similar to what we have seen for existentially quantified formulas. So this is the recursive computation. For the propositional logic of fragments, that's relatively straightforward. For existential box next, you first compute the set of states satisfying phi, and then you're going to say the satisfaction set of all the states that have at least one successor into phi. This must be non-empty, not empty. And this was a smaller set containing all the phi 2 states and all the phi 1 states that have at least one successor. And for existential box, it's the largest set that contain all the phi states, such that if you have a state in V, it also has to have at least one direct successor that goes to V. So this is the picture that actually I already drew on the blackboard. So what's the scheme of the computation? So remember, what is the characterization? The characterization, it's the smallest or the least set of states satisfying this criterion. So the easy way to do this is you first start fulfilling this criterion, yeah, by starting with all the states satisfying phi 2. So you're going to characterize all the states satisfying phi 2, and those are the states that satisfy your formula at first sight. This is the under approximation we're starting with. Suppose this is the set of states satisfying phi 1. Now what are you going to do? We're going to do a backwards reachability. So that means that the first thing we're going to do, we're going to check all those states that are satisfying phi 1, that have a direct successor here. They are going to be added to the set. Yeah. So I have the following formula. The set of states in the n plus first iteration is the set of states that I already have in the nth iteration, because we're enlarging these states. And we add in this iteration all the phi 1 states that have at least one direct successor that goes to the previously computed set of states. Yeah. And the way to see that is basically you have the following. So Ti is basically the set of states that satisfy, and I write this down syntactically, phi 1 until phi 2 in at most n steps. Yeah? So this, by this formula I mean really Yeah, so a state satisfies phi1 until at most n phi2, yeah, if and only if there exists an index k at most n such that basically this is a path, right? Such that this path starting at position k satisfies phi2, yeah, and all previous ones go here. For all I less than k, I have that sigma I satisfies phi1. What is important is this bound, and this bound intuitively, of course, comes back here. Yeah?
One small correction, shouldn't it be that the set is called Tn, not Ti? On the left, the name of the set.
Is this n? Absolutely. I'm still, I think, a bit off after the match of Wednesday, maybe. I don't know. I mean, I'm still. Yeah. Thanks. Yeah, this is n. Yeah, absolutely. Yeah. Yeah. Good. So what we have done is recursively we have already computed these sets of states. So this set of states is already at our disposal. This phi2 can be arbitrarily complex, but because of the bottom-up computation over the path tree, yeah, the set of that state satisfying this subformula has already been computed. So we really have this set of states, we have this set of states, and now we go back recursively by saying, okay, what are the phi1 states that have one transition into this set? And now you go back once more. You're going to add all the phi1 states that have a transition into this set that we just previously computed, and so forth, and so forth. Until you can no longer extend this set, and that means then you have computed the smallest set satisfying this formula. Yeah. Because we do this under approximation, we know that if we cannot add any state anymore, we have computed the smallest set. Yeah? And not another fixed point of this function. Good. So for instance, if you have like this here, we could have phi1 states, but they only point to themselves and they have maybe a transition outside. They will not be added in the end. So they will not be part of the formula of the set of states satisfying phi1 until phi2. So how does this work on a small example? So we have three colored states. I'm interested in the formula there exists a path which is blue until reaching a green state. Yeah. So how does this work? We start with the green state. That's our first approximation. All the green states satisfy the formula. Now we're going backwards. What are all the blue states that can reach the current set of states satisfying the formula, which is only this purple state here, with this purple circle? That means we're now going to add this state, because it's blue and it has a direct successor that is already satisfying the formula. So in the next step, we're going to add this state. Similarly, we go backwards. So now we're going to add blue states that have a direct transition to either one of those two states. So we're going to add this state and that state. This is happening here. Again, backwards, are there any blue states that we can add that have a direct successor to one of the purple states? And that's the case because this state has a transition to one of those states, so we add that state. Same question, is there a blue state that we can add because it has a transition to the purple states? No, not the case. So the computation terminates, and all the labeled states, all the purple labeled states, are the states satisfying the formula. Good. So this is how it works in terms of a pseudocode. You start with all the phi2 states. These are the set of states that you still need to, let's say, expand or grow. As long as this state is non-empty, we select a state and remove it from that set of states that we are still considering. For all its direct predecessors, we go backwards. So you look at the predecessors. if this state is a phi1 state and it has not yet in T, it's not yet already in the set of states fulfilling, the formula, then we're going to add it. And we're also going to add it to E because maybe one of those predecessors of the newly added state may also satisfy the formula. And then in the end, you return T. So that's all you have to do for existential until. Complexity of this algorithm is linear in the size of the transition system. Because you have to consider, in the worst case, all states, in the worst case, all edges, so it's the size of T. So how about always? So this is, remember, it's the largest fixed point. So what we do is we go basically starting from an over approximation, and basically from above we try to go towards this fixed point. So this is the largest set of states, such that this set of states includes all the phi states that have a direct successor into T. Good. So the thing we do is suppose that this is the set of states satisfying phi. Then this has already been recursively computed, so this is at our disposal. So how are we going to compute the set of states satisfying existentially box phi? The scheme is recursively, iteratively, starting by the set of states that satisfy phi and by iteratively eliminating states. So what is Tn plus 1? The set of states in the n plus first iteration is the set of states in the nth iteration that still have a direct successor in that set. Yeah? Good. So for instance, if this is the situation, suppose that those two states only have outgoing transitions that move outside this set T0, then it means that we're going to eliminate those two states in the first iteration. So that's exactly what happens. We're going to rule out those states. Now we can rule out those two states because those states have a transition there, but because those states are no longer satisfying the formula, they're no longer in our set, also those two states have to be eliminated. Good. And this goes back recursively as well. This state only has a transition there, that one has those two transitions, but both two states that do not and no longer belong to the set of states satisfying our formula, so we can eliminate them. We can eliminate this, and in the end you get something like this. You get basically something like a component which only, in this case, only moves to A states. It could still be the case, this guy may still have a transition outside, that would still be okay, because we're interested in that, does there exist a path which is completely blue, and that was the case here, because here we have an existential path which is completely blue. Good. So how are we going to compute this efficiently? So we start with the candidate satisfying phi, which was our first over approximation. Then we need all the states that can still be expanded. Well, what are the states that need to be expanded? Well, they're all the states that are currently not in T. As long as there are states that are not yet considered, pick a state and remove it from the set of states to be considered. Then we're going to look at the predecessors. If it has a predecessor in T, right, and S, this predecessor of S prime, has no transition to T, then I'm going to remove this S from T. So this is the situation. I go backwards. So here I have T, and I have a set of states that I still need to consider, so I take a state in E, which is something not in T, so it's somewhere there. So this is my S prime. Now I'm going to check for all predecessors, so for instance for this one, this is S. I'm going to check if S is in T, and it has no successors in T itself. So if this is the only one, or maybe another one there, but if it has no transitions into T, then I'm going to remove it. That was exactly the scheme we have seen. And then we return T. Good. We need to check this, and in order to do this efficiently, what we're going to do, if you do this naively, you get a quadratic time complexity. I would like to have a linear time complexity. So what we are going to do is we're going to use counters. And these counters are going to keep track of the number of successors of already considered states. So every state will get a counter C of S, and the idea is that the invariant will be that C of S is the cardinality, so it's the set of direct successors which move either into T or to E. So initially, T is all the phi states, E is its complement, so initially it's basically only the set of direct successors, because T unified with E is the whole set. And what we're going to do is we're going to, if we remove states from E, then we're going to decrease the counters. Yeah? And then we can easily check whether this holds by checking whether a counter is 0 or whether a counter is non-zero. So this is how it works. This was the frame we had before. We're now going to use those counters. As I said, the invariant of the program is that the value of this counter is the cardinality of this set. So initially, we have that T union E is the entire set. So initially, we just initialize for all states, for all phi states, we say that the counter is basically set to the number of outgoing transitions. So that's the loop invariant that was already anticipated. And rather than doing this check, we're going to check the following. If you have found a state which is in T, we're going to decrement the counter. If the counter is 0, we're going to remove it. Because if the counter is 0, it means it has no transitions to T states. Good. And this gives a complexity which is linear in the number of transitions and linear in the number of edges. Let's look at an example that maybe clarifies things better. So suppose I want to compute the set of states satisfying their exister part which is completely blue. Yeah. So for which states is that satisfied? Well, not for this state, because it can move here, but then it has to move to a yellow state. But for this state, you can move to the left, and you can move around here ad infinitum, and that would be a completely blue state. So let's see how the algorithm will compute this. We start first with having all the blue states. Yeah? Remember, we start with all the blue states, shrink this set by successively eliminating states. The first thing is we add those counters. Initially, the counters for all the blue states are just the number of outgoing edges. So this has 2 outgoing edges, so it just has the counter value 2. And now we start our computation. Yeah. So the first thing is we take a state which is outside the blue states. For instance, take this state. Yeah. Then we see that this state has a transition there, so we're going to decrement this counter, because the idea is that those counters are the number of outgoing edges going to blue states. Yeah. So this is 1, and that becomes 1. Okay? Now again, we take a state which is outside the blue states, so we look at this overstate over there. That means that this counter becomes 0, that counter becomes 1. So that's what's happening here. Now because this counter has 0, it means that this state has no transitions to the set of states that we currently have at our disposal. So this is the state that we have to eliminate. Yeah? But if we're going to eliminate this state, it means that this counter goes down to 0. Yeah? So this is what happens. We're going to eliminate that state. That counter becomes 0. Then we're going to eliminate that state, because all states that have counter 0 are deleted. This counter is becoming 1, but that's okay. And in the end, we have those 3 states satisfying the formula. Good. That's the whole principle. I think is relatively straightforward. Good. So the algorithm looks as follows. We have this recursive computation of the satisfaction set. For true, we just return S. For A, we just return all the states labeled with A. For negation, we take the complement. For conjunction, we take the intersection. And for existential next, you return this set of states that have at least one successor into 5 states. Here we had this procedure that I just showed you. This was you start with a set and you iteratively grow it until the set of states satisfying this formula. This has a linear time complexity. This was the algorithm I just explained with the counters, also has a linear complexity. So the total time complexity is linear in the size of the formula, because I look at all subformulas, times per subformula. The worst case I need to do is a computation which is proportional to the size of my transition system. So no exponential blow up like with LTL. No, this can all be done in polynomial time. Good, and this is in one slide the whole algorithm. Yeah, I skipped the propositional parts, but existential until is the union of all Tn's. Remember, you start with the phi2 states, and the next iteration, the Tn plus 1, is a set of phi1 states that have at least one direct successor moving to Tn. And this is the intersection, because we successively eliminating states of the Vn's, where we start with the phi states and then successively eliminate the states until you finally get a fixed point. Good, so let's look at a more complicated example. Let's not try to understand this formula, just look at this transition system, and this is the formula. What are we going to do? We're going to work inside out. Okay? So we first look at the subformulas. So for instance, we look, this is a subformula phi1, and assume that we have applied our procedure. Then the set of states satisfying this subformula are those 3 states, because those 3 states satisfy the fact that there exists a green path until I reach a blue state. What do I do? In the algorithm, we replace this formula by a new atomic proposition and change the labeling of the states. Namely, exactly those 3 states satisfying the formula will be labeled with this new atomic proposition. Let's assume this atomic proposition is purple. Then it means that those 3 states are now equipped with the purple atomic propositions. Yeah? All the other states are not equipped. I do the same with the other subformula. So I'm going to look at this subformula. There exists always not A. I apply the algorithm for exist box not A, and we find out this is the only state satisfying there exists always not A. I mean, this is also a not A state, but you see the only thing I can do is I moved immediately to an A state. This is also a state satisfying not A, but the only thing it can do, it can move here, and then you're trapped because the next thing you have to do is move to a green state. So the only state that satisfies this formula is that one. What's going to happen? We're going to replace this by a new atomic proposition. We are going to change the labeling. The only state that is now labeled with that atomic proposition is that state. For you, it's hard to, this is dark purple, this is, let's say, somewhat lighter purple, but this is, on my screen, it's better visible. This is another color. So that's the situation. Yeah. So now we go back one level up in our parse tree. So we have to consider there exists eventually the negation of these things. Okay? So what's a negation? Well, all the states that are neither labeled with dark purple nor with light purple, which is only that one, is now satisfying this formula. In terms of the algorithm, we're going to introduce a new atomic proposition, brown. The only state going to be labeled with brown is this state. Yeah. And that's the only state satisfying this formula. So now we have to consider, does there exist a path that eventually moves to the brown state? Good. And these are the states satisfying this formula. The initial state, because there is this path, this state itself, and of course this middle state. And those 3 states satisfy the formula. So at the end, I have computed that the state, the formula phi, is, if you go back, is satisfied by those three states, which are now labeled with phi. Good. Any questions on this procedure? So in this case, what you do is you first compute the set of states satisfying this formula, okay? So we recursively apply. Yeah? This gives us a set of states satisfying this formula, and exactly that set, all the states in that set, will be equipped with this new atomic proposition, replacing this subformula. Yeah? Good. So the complexity is linear in the size of the transition system and in the size of the formula. This is because of you take the path tree and you look at all subformulas and how many subformulas are there. Well, linear in the size of the original formula. And the size of T is from the fact that for existential until an existential box, the computation that you have to do is linear in the size of the transition system. LTL model checking, as we all remember, I hope, is linear in the size of the transition system, but exponential in the size of the formula. Yeah. For a fixed specification, then of course they are both the same. But the point is that if the CTL formula phi is equivalent to the LTL formula phi, then often, not always, often there are many cases where the size of the CTL formula is exponential in the size of the LTL formula. Yeah. And the example that we have seen already, therefore, was the Hamilton path problem. Yeah. The Hamilton path problem was encoded in LTL in terms of a linear formula, a formula of linear size, whereas for CTL, we had to basically enumerate all the permutations. You either start in this vertex and you look for a Hamiltonian path, or you start in that vertex and you look for a Hamiltonian path, and so forth. And this was an example that actually was there. So the general observation is that CTL formulas are often essentially longer, sometimes exponentially longer than equivalent LTL formulas, provided, of course, there is an equivalent one. Good. Yeah, there is more information on the slides, but that's basically about the Hamiltonian path problem, which is not so relevant to go into the details. Are there any questions? No? Good. Then we have a bit shorter lecture today. We're going to stop here for today. Hope to see you back on Tuesday. On Tuesday, we're going to discuss fairness. Sorry?
Will we only have like 3 lectures left?
Yes. So the topics that are left is fairness. I want to discuss CTL star, which is the logic that contains LTL plus CTL and more. And then we're going to see that you can combine the LTL model checking algorithm with the CTL model checking. And the last lecture is about what we have seen in the previous lecture, is that trace equivalence does not correspond to CTL. Yeah, but trace equivalence corresponds to LTL. So in the last lecture, we're going to see that bisimulation corresponds to CTL for finite, well, countably infinite transition system with finite branching degree, to be precise. Yeah. That's in 3, yeah. So I think it's the 10th of July, I think, yeah.